Hi, I'm Marciano Siniscalchi. I'm an Amazon scholar and a professor of economics at Northwestern University. This is joint work with Ming Chen at Outreach and Sarah Nabi, research scientist at Amazon Ads. This work is motivated by the observation that modern ad auctions are fairly more complicated than the simple models studied in textbook auction theory. So, for example, if we take as reference point the second price auction model studied by William Vickery first, there is a number of complications that we need to add in order to approach what the auctions that are actually run in the industry today. So the first is, of course, click-through rates, in consideration of the fact that per-click pricing is very pervasive, especially for search ads. Irrelevance penalties are commonly used to take into account the quality of the match between the user's search and the winning ad or the available ads. Hard floors are widely used in the industry. These are really what we call reserve prices in auction theory. But other mechanisms such as soft floors are also used in the industry, and these are quite a bit more complex. An important feature of online ad auctions is that, largely because they happen in real time, there can really only be limited feedback provided to advertisers in order to guide bidding. And in particular, most of the times advertisers really receive feedback about, their revenues, maybe their win rate, and certainly their cost of advertising, but they don't get the full feedback on, for instance, what every other opposing bidder bid in any given auction that is really underpinning standard equilibrium and learning theory analysis in game theory. And finally, targeting clauses are really of paramount importance. Namely, advertisers do not just decide how much to bid, but they choose what to bid on. And this turns out to change the strategic nature of the game quite significantly. So the bottom line is that modern ad auctions are actually so complex that standard equilibrium analysis is basically not feasible. So instead, we want to pursue a simulation approach. Our objective is to build a flexible tool that is a tool that allows us to study the impact of different ranking rules and pricing rules, take into account heterogeneity of bidders and so on and so forth. Given all these inputs, we want to be able to model and predict the strategic behavior of advertisers. And again, we want to do this in the setting of realistic ad auctions of the sort that are currently run in the industry. Here's a high-level overview of the model. The input is a distribution of bidders' types. And here we adopt the terminology of information economics. Okay, so what's a type? Well, in our model, this is a bidder's willingness to pay per click and a click-through rate. Okay, so it's this pair of numbers. A pricing rule specifies the price charged to the winning bidder as a function of all the bids placed and potentially other features. And finally, we also specify the shopper queries that might come through and that are relevant to the auction under consideration. We'll provide more details in a second. In each simulation round, we first draw bids and later targeting clauses. We compute the price on the basis of the realized bids. We observe for every bidder the reward, which is 0 if the bidder does not win, and the click-through rate minus values minus price times, value minus price in case the bidder I is the winner. Given these rewards, the learning algorithm updates the bid probabilities, and then we go back to the beginning. We iterate. The outputs of the simulation are, at the most granular level, the bid distribution. But of course, we can also compute from the bid distribution other metrics of interest, such as revenues, cost per click, conversion rates, and so on and so forth. Throughout, we use a collection of principled learning algorithms meant specifically stochastic fictitious play. This is well known in game theory. But for today, I'm going to focus on two well-known algorithms from the literature on online learning or reinforcement learning, namely hedge, which is an example of a full information algorithm, and EXP3IX, which is an example of a bandit algorithm. Okay, we'll see what the differences are. I'm going to describe two applications today, and I'll refer you to the paper for details. The first is an analysis of the soft floors mechanism. So what's a soft floor auction? Well, it's basically a second price auction, which, however, switches to first price auction if the winning bidder is below the soft floor specified by the seller. In an influential paper, Zeithammer in 2019 conducts a Bayesian Nash equilibrium analysis of soft floor auctions and is able to obtain a variety of partial results. With symmetric bidders, soft floors are ineffective. This is really just a consequence of the revenue equivalence theorem. It's a well-known fact about auctions, standard single object auctions. With asymmetric bidders, things are a little more interesting, and Zeithammer considers a variety of special cases. And essentially, what I want to draw the attention to is the fact that there's at least one important case, and that one of what he calls a deterministically stronger bidder, say a dominant player in an industry facing smaller competitors, where it is just not feasible to compute equilibrium bidding and derive equilibrium revenues, right? So instead, we want to take a simulation approach, and specifically what I want to talk about today is our simulation of multi-query auctions, right? So we want to take seriously the fact that, as I said earlier, advertisers specify which keywords they're bidding on, and these are called targeting clauses. The user queries are matched to relevant keywords, right? And the point is that the same keyword, as a result of being matched to different queries, may actually have different CTRs and different values, right? And so this really changes the strategic nature of the game, right? And so we want to model specifically the fact that in addition to a bid, the bidder can choose a targeting clause, namely the set of queries that the bidder allows to be matched to their ad. So you can look at the paper for the details. We report the results of a simple experiment with 2 queries and 3 bidders. The queries are all equally likely to occur. The values of the CTR are as in this table. Numbers are not so important, but the main findings are that with a long enough learning period, with fine enough bit grid, we show that, number one, revenue equivalence does not hold, even though this is a symmetric environment. Namely, the type distribution is the same for all players, for all bidders. And in particular, sometimes the soft floors may actually provide higher revenues than the second price auction. However, importantly, different learning algorithms have different implications. And so we decided to also dig more deeply into this, because we think this is a sort of interesting finding both for theoretical and applied reasons. So here are the results as far as the bid distribution is concerned for the second price auction under the hedge algorithm. This is a full informational algorithm which updates bid probabilities based on the rewards from all possible bids and targeting clauses for all actions, namely both the actually chosen one and the counterfactual ones. So what you can see here is that every bidder type essentially decides on one targeting clause, which may be to bid only on query 1, only on query 2, or on both query 1 and 2. And then within that targeting clause, they basically converge to one number, okay? Now, this is what happens instead with EXP3IX. This is a bandit algorithm which only uses the rewards from the actually selected action, okay? So much less feedback, essentially. Now, as you can see here, there are a lot more bids that are used, even sort of quote unquote in the limit. And moreover, every bidder and every type of every bidder is really targeting all queries with a positive fraction of bids. So takeaways: choice of algorithms matter. But more importantly, the bandit algorithms do seem to learn way more slowly in realistic settings where the bid grid is fine and there's this additional dimension of what to bid on. Yet we like them because they are more principled. And so, the question is, what to do with this finding. And we have some observations and suggestions in the paper, but certainly we'd like to conduct more research on this topic. Second application I'm going to talk about is value inference. So this is actually something that is very common in empirical industrial organizations. And the idea is we are given the aggregate bid distribution for some collection of queries, perhaps. We want to infer the aggregate distribution of advertisers' values, right? So now notice that the values really exist in the mind of the advertisers. They're not directly observed. So how is it possible to derive these values if all we have to observe are the bids? Okay, well, with standard auction formats, this is easy to do. And the bullet points here provide indications on how to do so. Again, this is a standard exercise within empirical industrial organizations in economics. But what about real world auctions that use formats that are not first price or second price? Okay, we cannot solve for the equilibrium. So what are we supposed to do? Well, our suggestion is to use a simulate and iterate approach. We provide examples based on real world data from a low traffic keyword auction and a high traffic keyword auction. Low traffic means few advertisers bidding. High traffic means lots and lots of advertisers bidding. You can look at the paper for details. What you want to see here is that convergence of the value distribution happens after a relatively small number of iterations. Okay, you can also see that it is important to postulate a pricing rule. So you sort of gotta know what the pricing rule is in order to conduct, this exercise. And again, in this case, we're just assuming second price, first price, and software auctions. Okay, we're just postulating that. In the high traffic keyword example, we use a quote unquote realistic pricing rule. Cannot provide more details, but again, the key takeaway is the same. We get convergence in relatively few steps. Again, conclusions, we simulate advertisers' behavior with principal learning algorithms. We can perform what-if analysis, as well as infer advertisers' willingness to pay, and more. Thank you very much for your attention.